Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Science Thursday, we're going to talk about CO2 refrigeration system or R744. So let's dive deep into it. So why do we need this puppy? Well, simple reality is we need better refrigeration systems, and the need for that is growing like exponentially, so to say. And because again, earth is heating up, so the amount of people who need air condition to survive is going up exponentially, and as it heats up more, the more load would be fall on to that cooling system. So we need something that is good. Now here's the deal, what are our criteria list? So our criteria list is that we cannot be flammable or toxic. Now flammable part kicks out butane, toxic and flammable part kicks out ammonia. So those two are the most amazing thing, but this is the final penalty of this is like, we want something that is not flammable nor toxic, and ironically that's how we fell into the trap of Freon. But we have to learn from that, and it should not affect the environment. We have learned the hard way that's why we are focusing so much on natural elements or natural compounds, because nature inherently, if it's a natural, exists in nature, it knows how to handle it. So we want something that is fundamentally does not give a damn about environment. Like if it leaks into the atmosphere, we should not care about it. If it goes to the ozone layer, we should not care about it. So it should have no negative effect on either O3, ozone, or greenhouse effect. Now here's the deal, does greenhouse effect matter? Well, yes, some of the gases that were used in the refrigeration cycle were so potent because CO2 is classified as 1. To give you a context, there are some gases who are much worse than that. For example, methane is one of the naughty ones. That puppy goes up to 20x the greenhouse potential. So we do want to make sure that even if you are releasing small amount, it should not be more worse than CO2, because again, CO2 release is like, we are breathing out CO2. So it's not that big of a deal. But you do not want something that is like, global warming potential of like 50. Even a small amount of it will cause cascade failure. So we want to make sure that greenhouse potential is almost zero, and ozone depletion potential is also zero. And it has to be cheap. Many of you are not familiar with the fact that when the Montreal Convention was signed, there were certain, let's just say, miscreants into that. Certain bad elements were put into it. For example, so every country got together and they're like, okay, we have to replace this. But here's the deal, who has a refrigerant? That time certain Western companies had that refrigerant. They had it patented. And the idea was every country that signed that memorandum has to buy it from there. But here's the deal, company knew that because if they had this sort of monopoly, other countries will simply just like, lol, I will keep using the system. To make sure to incentivize this sort of compliance, they made sure that World Trade Organization will kick you out if you do not follow that lead. So that was a very bad lesson. And again, that's why even though we are going more greener technology, richer always gets richer. That's why. So this time we learned our lesson. It has to be cheap so people actually use it. So again, another benefit of using natural thing, there is no patent, nobody gives a damn about it. So that's what we need. So R744, it's an old puppy. So it was known and tested from 1860s, not 1960s, 1860. That's how we used to make banners back then. So ancient technology. This is a very ancient technology. But here's the deal, if it was that old and it has all the criteria like no flammability and no natural hazard, why the heck we did not use it? Well, it did come with one giant penalty, which was this puppy. It was idiotically high in terms of pressure requirement, meaning, to give you a context, that time, like as in like in 1860, it was like, it's a miracle that you could even achieve that sort of pressure reliably. I mean, you can achieve very high pressure, it's just that can you do it reliably long enough? So that was the whole point. To give you a context, another refrigerant used in that time was propane. Again, very good propellant. Refrigerant, it only needs 12 bar, that is 174 psi. So even a normal refrigerator compressor can easily go up to 200 psi if it's designed for that. So it's not an issue, it's just like take it and go. But the moment you go to CO2, that puppy starts at 130 bar. That translates to 1900 psi. That's a lot of pressure, like ludicrously large amount of pressure. And it does come with two risks. One of the risks is asphyxiation risks, because for example, let's say this is my indoor place where I'm working. I have this air conditioner. Let's say it's filled with a giant amount of CO2. What happens if it leaks? It will displace the oxygen here, and the fact that human body starts to malfunction at around 10% concentration to 15% yet aid. So fundamentally, we have to make sure that this does not leak, or you must have a HVAC system which pumps enough fresh air that even if it leaks, it does not reach that 3 or 5%. Now, good part is it's not carbon monoxide, so it's not as hazardous as that puppy. And asphyxiation technically can happen with any gas. So if you have too much nitrogen leaking in, yeah, that will also have that same effect. You lose oxygen and you pass out, and then you get permanently passed out. So that's a very low level thing. It's like gas dumped into another volume. It's one of those things. And again, thankfully, human body knows how to deal with CO2. So even if, let's just say, you are in a room, you really started to notice, hey, wait a minute, I think CO2 is leaking here. You run away to outside, your body will flush it out. Do not have to worry about it. Another benefit of natural aspect. Another aspect is high pressure risk, because again, if 200 psi compressor goes boom, that's a minor inconvenience. Annoying, loud, minor. But if 1900 psi compressor goes boom, that's a major oops. So fundamentally, it does require certain level of care. Now, is that a big deal? It used to be, not anymore. Why? Well, if you come to India, we have something known as CNG, compressed natural gas. That puppy starts at 300 bar. So we good. We got this. We trained on this. And the people who are smoking hydrogen, those puppy requires up to 600 bar. So 130 bar nowadays in modern technology after 2020, it's like, who cares? So those two risks have been alleviated. Another aspect is one of the most safest refrigerant, and in many regards. Basically, if you have fire, many refrigerant release such a carcinogenic agent, you'll be like, bro, no. CO2 puts out fire, so it's like fireproof. Another benefit against ammonia and propane, butane also. So no fire risk. That's the good part. Natural. Even if it leaks, you do not have to have regulations and air monitoring sensors and all that. You do not need to worry about it. So that does not be. And again, no global warming potential and no ozone depletion potential. So we do not have to worry about it. And if you are uber rich, your car may already have this. Certain level of uber hyper rich cars have this. 744 as a refrigerant. Now, let's understand the cycle of it. Now, you have to understand this. There are cycles, like normal refrigeration cycle, super easy. You have your things, it gets compressed, it dumps its heat into the ambient, then it condenses into liquid. Liquid goes into a system where it goes through expansion valve and then it cools down. Okay, so we call it evaporator, and then cycle repeats. Everything is fine, everything is dandy. Here it's not like that. Here is not that simple. It's ludicrously complex. So to give you a certain vector for it, you must have studied in school that CO2 does not become a liquid on Earth simply because atmospheric pressure is not high enough. One atmospheric pressure is 1 bar, 15 psi. So if you had 32 degrees Celsius material and it was under 74 bar psi, or like a 1070 psi system, so to say, so that will only allow you to reach supercriticality. You will not be in a stable state. It will neither be fully solid, neither it will be fully liquid, neither it will be fully gas. It will not be in a stable state. It will be somewhere in between liquid and gas. So you can understand it's a supercritical system, exactly like supercritical CO2 turbine. So it does not basically have clear state change. We say like, oh, it's liquid now, oh, it's gas now. No, it's a supercritical, subcritical, supercritical, subcritical, transcritical. So it's like that. So CO2 does not have easy state change. Like it's very difficult to do that. And transcritical simply means it enters the condenser when it is supercritical state, returns subcritical, but still not liquid. So that's one of those things. And the reason why CO2 can still work when it's not going through those simple phase change and latent heat of vaporization is that it has very high vapor density, meaning the amount of oomph it can carry from gas state to gas state, it's very high. It's actually, you can keep running a CO2 refrigeration system without having phase change and it will still work. It will not be great, but it will work. So that's one of the unique advantage of CO2. So that's how it works. And because of the mess involved here, going from basically supercritical to subcritical, that's why the system is called transcritical, requires multiple stages and multiple compressors. Now, let's dive deep into it. So I would urge you to relax, chillax, turn the AC on because this is messy. So we start with your main compressor. We call this puppy medium temperature transcritical compressor. So these compressors are sucking in CO2 from the system, creating a negative system in the things below it, and then you pressurize the hell out of it. Then you dump it to condenser, which again, general terminology is not condenser, it's a gas cooler. They just call it condenser because AC technicians are used to that. So it's gas cooler because hot supercritical gas goes in, hot gas is gone away. Now you have subcritical cool gas. So that cool gas, still gas, let that be very clear, it's not liquid coming out of here. That's why it's gas cooler. And that's the primary benefit of this technology, is that because this compressors push the temperature so high, and again, CO2 does require bonkers high pressure, the temperature also goes up. Meaning this puppy can dump heat into the ambient even if ambient is India. 50 degrees Celsius or 60 degrees Celsius, this puppy can almost touch 70. So gas cooler will still dump all the heat, and then you come into basically high pressure control valve. Now this control valve dumps all the cool gas, so to say, into what we call flash tank. So you must have studied this in your air liquefaction section. Basically you take the air, you compress the hell out of it, you cool it as much as you can, and then you expand it, it becomes into a liquid. Same thing happening here. So CO2 comes here, you have a volume of space where you're just letting a small amount through due to pressure relief valve. What happens? Pressure drops exponentially. So some amount of CO2 becomes liquid and some amount still remains gaseous. Like, nope. So the gas goes again into the compressor system for recycling, and then you have that liquid CO2. Again, I said it goes into lower pressure. Lower pressure according to this system, not lower pressure here. It's still high pressure there. So that liquid goes into two subsystems. In this design is two subsystems. So you have lower temperature display cases. So there you will have, let's say, minus 30 degrees Celsius refrigerant coming in, and it will expand, it will do its job, and it will be still would be low potential. It should still have enough capacity to absorb heat. So they take that, dump it again into flash tank. So in flash tank, there is a heat exchanger that allows it to boost its refrigeration efficiency. So that low pressure, low temperature refrigerant will go into low temperature subcritical compressor. Now the reason why you directly do not want to pump this puppy here is because these compressors will give up on life. So you have to pre-charge them. So once you have these very low pressure gas, you just boost it up. So basically, let's say here it could be as low as 100 psi. You are like, okay, let's put it 500, 600. So this compressor can work without frying itself. So you have this, and then you have another line that will go into medium temperature case, or in this sort of scenario, it could be air coolers. Basically, that refrigerant is boiling in the air cooler, and you're not dropping the temperature, but you are dropping a lot of heat. So you're dumping a lot of heat. So that heat goes into your medium temperature transcritical CO2 compressor, and then cycle repeats. And again, there are two primary factors why the systems are adequate for shop scenario, basically malls. Malls love this because again, they do need both cooling system. They need a very cold cooling system and they need medium cooling system, and both of them can be separated quite well and controlled individually also, meaning you can make sure this goes very low temperature, this goes not that low temperature. That is doable. And again, that's why the graph will always have this weird dip because of this thing. So it is a complex cycle. And again, condenser is not condenser because there is no condensation happening there. You have gas cooler. You have very high temperature supercritical gas going, and very low temperature subcritical gas. And again, low temperature being close to ambient. So let's say ambient is 50. That temperature could be as low as 55. Let's just go with that. 55. That 55 you expand, it becomes your liquid. Liquid goes only as low as minus 35, maybe minus 40. And then you do your system again. So that's the cycle. And again, that's why you need multiple compressor and multiple stages, so to say. Here you can easily see two stages. And some systems have even more or more compressors. Now, the biggest penalty of this puppy is complexity. And you know about engineering, complexity is the enemy of reliability. This thing is messy. It requires completely new infrastructure. And this is the only thing I've seen in terms of complexity that beats ammonia circuits. Ammonia circuit is messy. It's just like a lot of liquid, lot of oil separators, lot of this and that. But it's inherently the same thing. Here it's like, no, no. Most people are like, what the hell is a flash tank? So it's a completely different ballgame. And it does require safety and stability at high pressure, meaning all the plumbings have to be designed in such a way that you have very high temperature supercritical fluid going through it, which is let's say 150 degrees C, does it expand, does it contract, how does it handle that, and again, how does it handle it 10 years from now, 15 years from now? So this does require complete new infrastructure thinking. So that's a messy part, and it does have one of the most complicated valving system I've seen. I've linked this video down below, and trust me, it will fry your brain. It's like, what the hell? It is messy. It is very messy. And again, without this valving system development, we may not have even tried to run these things on basically hotter climates. But again, European Union and Japan was trying to use this system quite early on, like as early as like 1990s and 2000s. But they soon kind of realized that if this system is only good at like 30 degrees Celsius, it's not going to be useful for long. So they worked on this sort of multi-stage design, multi-injector work systems and all that to make sure that this can work at high ambient. And benefit of that is now we can find this technology that it is very well suited for hot climates. And plumbing is very complex. While ammonia does have a plumbing where it's like, oh, you have to ammonia pump and pump that, this plumbing is like, okay, we have low pressure going back to the top of the building where the flash tank is dumping heat and then coming back. It's like, what the hell? It has a lot of stuff, lot of plumbing wise. It's still like mess. And again, it does require heavy tank, because that tank, even though it has liquid CO2, it does have very high pressure still. Pressure is a relative there, so it's still dangerous. And again, not to mention, any crack, it will expand instantaneously, so it will be kaboosh. So that's a very big thing. And it can work well if it's below 30 degrees Celsius ambient, but here's every other refrigerant will beat it. If you are, outdoor is only 30 degrees Celsius and let's say you only need to cool to 25 degrees Celsius, yeah, it does not matter at that point. At that point, use propane, butane, ethane, whatever have you. But transcritical system, again, when you have that sort of mixing and you call it gas cooler, you can achieve a high heat rejection at a very high temperature, aka 40 to 60 degrees Celsius. That's the big thing of it. And it also makes a heat recovery viable. For example, let's say you're running it on a hotel system and you want to get hot water out of it. Normal refrigeration systems do not like, if you are like, hot side, you want to be very hot. Like let's say you want 60 degrees Celsius water. Yeah, it's like, no, we're only going to give you 50. So this puppy is like, bro, I got this. Me good, I got this. It makes it viable. Thermal energy recovery becomes a viable. Heck, I would not be shocked if somebody actually figures out how to put some sort of a thermal energy conversion unit into it. So that can be done, like a Stirling engine. So that's there. And it's not a magic bullet, let that be very clear. While CO2 does have this one advantage, everything else sucks. And again, given in the same constraint, all other system will beat it. That's why we have not been using it. And again, all the complexity requirement and the new cost and new infrastructure, that is there. And it does require completely thoroughly trained workforce. The workforce has to be retrained thoroughly, because you cannot be lolling around, because the moment compressor turns on and if there is anything that is causing a blockage, or if things are not done correctly, this could even have the side effect of having CO2, aka dry ice formation, that could cause cascade failure. So it has to be taken care very seriously. And it has not reached mass production yet, because again, it only makes sense for large units. So it's a messy thing. And again, this thing looks like black magic. So what can we expect in the future? Well, it does have one true advantage, which is genuinely a good thing, because right now in India, a lot of AC manufacturers saying we can survive at 55 degrees Celsius. I'm like, bro, we're touching 60 degrees C. Come on. This can handle that. So that's the good part. That does make it desirable. And cost is not that great. That's the painful part of it. And new technology, safety, and all of that jazz. And then we have the daddy, which is ammonia. Ammonia is like still king, because ammonia can go up to 100 degrees Celsius. So it's like it can dump heat at 100 degrees Celsius. And if you have higher than 100 degrees Celsius in daytime, you have other problems. So it's like, bro, that's why ammonia was there. Ammonia is there. Ammonia will be there. It's one of those daddy. And again, it has ludicrously high thermal capacity, so to say, because of 1290 kilojoule of energy per kilogram. It's bonkersly high, and it does go through phase change. CO2 does not go through phase change. CO2 does have that benefit that it can work as a gas system, but it won't be very high COP. COP will be as low as like 1.3. So that's the reason. And mixing both gives you best of the both worlds. For example, let's say you have a giant building complex or a giant mall, and you want to cool it as efficiently as possible. Well, ammonia is your guy. So you use ammonia, but here's the deal. You have a lot of people inside. You do not want to A, smell bad, B, have a risk, has a health hazard risk. So you isolate that puppy. You isolate that completely outside. It's like, no, it's like a high voltage transformer. Nobody goes near it. Nobody has to worry about it. It's completely sealed, and you might keep it in a little bit of negative pressure. So even if your ammonia leaks, it directly evaporates away. So that's there. Completely outdoor, low charge ammonia. Everything is fine. Everything is dandy. Very efficient. Awesome. But how do you circulate it? Because again, you do not want to circulate ammonia inside your building. So what do? Well, you can dump energy into water and run water there, or you can rule another system, CO2 system. CO2, when the cold side, aka the evaporator condenser cycle system, the condenser is actually below ambient, let's say 0 degrees Celsius or minus 10 degrees Celsius, it works efficiently well. Like at that point, it works as well as every other system. And then you can directly go through normal CO2 system. And because of high pressure of CO2, CO2 can cycle through much larger area. And again, if CO2 leaks, nobody will freak out. People will become bit lethargic. And you can easily detect it with sensors and all that and evacuate the system without too much hassle. Evacuate simply meaning you pump more fresh air in and shut down the system. So this way you can get best of both worlds. You have the very high capacity of ammonia working outdoor, completely away from people, and then you can have CO2 working, which is relatively harmless, because again, the alternative is you can use butane, which again, in this sort of scenario, butane will be daddy, like it would be really efficient. It's just that butane, it burns, and propane is also the same, it burns. So you want something that is non-flammable, non-toxic, only the CO2 meets that criteria. So this is the best of both worlds, because again, neither of the system is easy enough where you can put that in household. So ammonia stays outdoor, CO2 stays indoor, and you get best of both worlds. So this is a system, again, I've linked to one video down below where one mall sort of structure have already done this. So this is how I see future unfolding. So this was my presentation on basically CO2 as a refrigerant. Hopefully you have liked it, learned from it. In that case, please click the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show me extra disappointment. Please leave a comment because I do try to reply to all of them. Subscribe, press the bell icon if you're free. And as always, thanks for watching.